Hi, today I'll be calculating the density of a log in a lake. And so some things to know before we start are some equations. And so the buoyant force is equal to the force of gravity of this log, which is labeled with L. And then the assumptions is that this log in the lake is a perfect cylinder. So let me draw this situation out first before we get started. So we have our log, which we're going to assume is a perfect cylinder to help approximate, and it's under some water, right? So all you could see would be this top part out of the water. So let's upscale this and start labeling things. So we have some radius r, and then here's the height of this water on the log, and then the height of this will be labeled as h, we'll label this as r, and then the length of this log will be labeled as L. And so, as I said earlier, the buoyant force is equal to the force of gravity from this log. And so this will be the mass of the water times the acceleration due to gravity is equal to the mass of the log times the acceleration due to gravity. And so from here, we can see that the mass of the water is equivalent to the mass of the log due to the fact that these g terms cancel out. So we have m sub w is equal to m sub L. And then from here, we can substitute in for m sub w and m sub L. So we're going to have the density of the water times the cross-sectional area, which is any area on the log below, like that is under the water, times the length of the log, is equal to the density of the log times, and so since it's the log, it's this whole circle, so it's just going to be, the area is going to be pi r squared. So times pi r squared, and then times the length of the log. And so from here, we can see, similar to up here, we have terms that cancel out, so the length of the log doesn't affect anything later on, so we can just cancel those. So from here, we have the density of water times the cross-sectional area of the water is equal to the density of the log times pi r squared. And so what we need to do is find the cross-sectional area of the water, of the log that's under the water. So, because the density of the water is a known value, which is 1,000 kilograms per cubic meter, and we need to solve for A so we can isolate and later solve for the density of the log. So that being said, let's get this circle and redraw it. So as you can see here, we have some radius r, the height of the water, and then just redraw that because that'll be helpful later when calculating the cross-sectional area. So then we'll have some same angle theta, and then this up and down length will be labeled as r minus h. And so what's really happening here is we are solving for this, which is that, right? So this equals the total area of the circle minus this top part. But what we run into is we don't know what this top part is equal to, so we got to solve for that. And that's what this is right here as well. So that is equal to that. So we're taking this sector and then going to subtract the triangle so we can be left with that. So we're first going to do this to then solve for that. And then once we have this area, we can subtract the total area of the circle from that to get our desired cross-sectional area, which we can then plug in right here. These two are equivalent. So that being said, let's first find this area right here. So we're gonna have 2 theta, there's 2 of them, and then 2 pi radians, we're gonna divide by 2 pi, times pi r squared. So this is equal to, so 2's cancel, the pi's cancel, theta r squared. But we don't know what theta is, but through trigonometric rules, we can figure that out. So this being said, we are given an adjacent and a hypotenuse relative to this angle theta. So theta is going to equal inverse cosine or arc cosine of the adjacent over the hypotenuse, which is r minus h over r. And so with this, we can now plug this theta back into here and get this area. So what we have there is r squared arc cosine of r minus h over r. So that value right here is the area of this. And so now we need to find the triangle, which is right here. And so with that being said, we know the area of a triangle is half the base times the height. And so we need to know the base. So we'll just label each side as x. And we're gonna first find the area of one of the smaller triangles and then just double it to get the big triangle. So we'll just write that out. We got half, we labeled our base as x, and then times the height of the triangle, which is r minus h, that adjacent side that we talked about earlier. So this right here is the area of one of these 2 triangles. But what we need to do is solve for x. And so we know x is one of the sides, r minus h and r, so we can use Pythagorean theorem to solve for x. So we have x squared plus, and then we have r minus h squared equals r squared. So then when we solve for x, that's going to equal the square root of 2rh minus h squared. So then we're going to take that value, plug it back in there, and then multiply that area times 2. So since we're going to be multiplying this by 2, this 2 will, and times 1/2 will just equal 1, so they'll cancel. So all I'm going to do is multiply that base of x times r minus h, and that'll be our area. So that being said, we have 2rh minus h squared. So that's our x value times r minus h. We draw that. So this is the area of this triangle. So what we're going to do is take this value and subtract it with this value. And then from there, we will get this. And then once we get that, we can subtract the total area of the circle from that. And then we can get our desired cross-sectional area of the log under the water. So once I get more room on my whiteboard, I'll continue and we will finish up the problem. All right, now that we got the area for this, we are going to subtract the total area of a circle, which is just pi r squared, which you can see right here, and then subtract it from this area, which we found to be r squared times arc cosine of r minus h over r, minus the quantity of radical 2rh minus h squared times r minus h. And so that is this area here, which is the area of the log under the water, which is seen right there. So we'll rewrite this equation. So So the density of the water times the cross-sectional area equals the density of the log times pi r squared. So now we have this A value, which is right here. We know that the density of water is 1,000 kilograms per cubic meter. So basically what we're gonna do is multiply this by 1,000, and then what we're gonna do to isolate the density of the log on one side, we're then also going to divide that by pi r squared. So what this density of the water will look like, rho L equals 1,000 times pi r squared, the total area of the circle minus this top part, which is above the water, the area above the water. So then that'll be r squared, r cosine r minus h over r. Then that is then subtracted by the quantity of radical 2rh minus h squared. See there, then times r minus h. And so now we have the 1,000 for the density of the water times that area, and now we're just going to divide the entire thing by the area, the total area of the circle. So that'll be all of that over pi r squared. And so now we've calculated the density of the log.